Up to this point, we have assumed that any bit vector stored inside the computer represents an integer, possibly encoded in such a way that its sign can be explicitly determined. However, a bit string can also represent a real number. We therefore begin by studying fixed point notation, so-called because the position of the radix point within the bit string is fixed and identical for all numbers under consideration. This partitions the bit string into two parts: a predefined number of bits for the integer part and a predefined number of bits for the fractional part. In fixed point notation, the position of the radix point is implicit within the numerical representation. Therefore, it is not explicitly stored or represented in the bit string. The position of the radix point in a fixed point binary representation corresponds to interpreting the bit vector as an integer value multiplied by a scaling factor. If we consider a bit string B composed of k bits for the integer part and n bits for the fractional part, the scaling factor is equal to 2 raised to the power of minus n, and the numerical value of B as a fixed point value is equal to the integer interpretation of the bit string multiplied by such a scaling factor. Alternatively, we can view the representation in terms of positional weights. The k bits that represent the integer part are weighted with increasing non-negative powers of 2, from 2 raised to the power of 0 up to 2 raised to the power of k minus 1 as we move away from the radix point. Meanwhile, the n bits of the fractional part are weighted with decreasing negative powers of 2, from 2 raised to the power of minus 1 down to 2 raised to the power of minus n, again moving away from the radix point. Let us consider the following example, in which we want to determine the value of a string of 8 bits, encoded in fixed point notation and using 5 bits to represent the fractional part. The vector B is 0, 1, 0, 1, 0, 1, 1, 0. If we place the implicit point between the 5th and the 6th bits from the right, we interpret the bit string as 0, 1, 0, radix point 1, 0, 1, 1, 0. We begin by interpreting B as an integer. The result is 86. Next, we compute the scaling factor, which is 2 raised to the power of minus 5, obtaining 0.03125. Finally, we multiply these two values, obtaining the result which is equal to 2.6875. The equivalent value of the fixed point representation can also be obtained by considering positive powers of 2 for the integer part and negative powers of 2 for the fractional part. In this example, the second most significant bit has weight 2 raised to the power of 1. The fourth bit has weight 2 raised to the power of minus 1. The sixth bit has weight 2 raised to the power of minus 3, and the seventh bit has weight 2 raised to the power of minus 4. By summing all these weighted contributions, we obtain 2.6875, exactly as in the previous case. The sign in a fixed point number can be encoded using the two representations previously introduced, sign and magnitude and 2's complement. Let us consider the bit string 11010110 as an example, assuming 5 fractional bits. In the sign and magnitude representation, the most significant bit represents the sign, in this case negative, while the remaining bits define the magnitude. Each bit equal to 1 contributes according to the power of 2 corresponding to its position. Summing these contributions and applying the negative sign, we obtain the value minus 2.6875. In the 2's complement representation, if the most significant bit is 1, then it has negative weight, equal to the corresponding power of 2 with a minus sign. This contribution is then summed with the remaining positive weight terms, computed as usual. The resulting value is minus 1.3125. All arithmetic operations on fixed point numbers are performed exactly as if the operands were integers. Therefore, the same arithmetic circuits can be used. The only aspect that must be carefully considered is the implicit position of the radix point. For addition and subtraction, the operands must share the same radix point alignment in order for the operation to be valid. For multiplication, no prior alignment is required. The effect of the radix point positions of the two operands is naturally reflected in the result. The radix point position of the product is obtained by adding the number of fractional bits of the two operands. A similar rule applies to division. The radix point position of the quotient is obtained by subtracting the number of fractional bits of the divisor from that of the dividend.